dear President and members of the jury, friends and fellow researchers, thank you very much for your virtual presence and welcome to my PhD defense. My name is Anthony Choppa, and today I am pleased to present my thesis entitled Real-Time Semantics in Video Sequences, both live on LiveSize and on YouTube. And I'm really happy to see that we are almost 50 to attend this meeting, so thank you very much for that. In this presentation, we will go through many interesting topics across the fields of computer vision and deep learning with a focus on soccer games. All right, if you're ready, let's jump right into it. My main goal will be to give you the keys to extract meaningful information, also called semantics, from videos with real-time methods. For that, we separate this notion of semantics into two levels, low and high. The first one focuses on the description of the scene. So for instance, where the players are and how they are moving. Then, high-level semantics relates more to the interpretation of the events that are occurring during the video. This can be spotting different game events and linking them to understand what is happening in the game. As you can probably already imagine, all these different semantics are very important for many applications and particularly for the soccer industry. Let's give a few examples. As you may have noticed with the COVID-19 pandemic, it has drastically changed our perception of sports. Without the fans in the stadium, the games feel somehow tasteless. To counter that, some leagues came up with crazy ideas, like virtually including fake supporters and stadium sounds with screams and songs. All this could be improved further with the help of intelligent computer-aided systems. Another interesting application would be the automatic production of TV broadcasts. Automatically selecting which camera to show on TV would really ease the work of the broadcast producer. And with that, each viewer could have a personalized experience based on his own preferences. As a last example, if you know where the players are and where the center of attention is located, you could automatically pilot the cameras to follow the action. This would drastically reduce the production costs, which might allow smaller leagues like 3rd or 4th division to provide the same kind of TV content that only the richest leagues are able to afford right now. So as you can see, there is both an economical and a social impact in developing automatic methods. All right, so what are we going to see in this presentation exactly? We'll start with the extraction of low-level semantics, all the way up to high-level semantics. First, we'll look at motion detection, then player segmentation and detection, aiming to perform these tasks in real time, which means at the original pace of the video. For that, we developed some quite innovative methods. From there, we'll see a very simple way to use low-level semantics to extract different game phases. And we'll show how to leverage the temporal context directly inside a deep learning model to spot different actions in the game. Finally, we'll present a whole new dataset for soccer video understanding. All right, let's start our journey with motion detection. The objective is to segment all moving parts of a scene by classifying each pixel into one of the two following classes: the foreground, containing the moving objects, and the background, for the static parts. There exist many algorithms to perform this task, but the problem is that they are either fast but not that good, or very performant but also very slow. For practical applications, it is important to meet both the speed and performance criteria. What we propose is to leverage the best algorithm in each set. So VIBE for the fast algorithm and semantic background subtraction, also called SBS, as the best performing one. We started with the semantic background subtraction method that combines any motion detection algorithm showing where the motion is in the video with white pixels with semantic segmentation to produce some high-quality motion detection. Just for the ones that are a bit less familiar with semantic segmentation, it simply consists in assigning a unique label to each pixel, representing the class of the object it belongs to. So in this example, the person is in yellow and the door in blue, and so on. So for each pixel, the motion detection algorithm predicts if it belongs to the background or the foreground. Then, a new semantic classifier also estimates if the pixel belongs to the foreground, the background, or if it simply doesn't know, based only on the semantic segmentation. So for instance, if a pixel was classified as a tree, it is most likely in the background as, trees are not moving. Counterwise, if it was classified as a human, it could belong to the foreground. This combination always trusts the semantic classifier when it makes a prediction, which is shown in red just here. And only when the semantic classifier doesn't know, does it trust the motion detection algorithm, which is shown in blue. In theory, this method works very well, and it has shown some state-of-the-art performances. But in practice, when you need to treat all frames of the video in real time, not so well anymore. The issue is that it requires both the motion detection algorithm and the semantic segmentation to work in real time. For motion detection, that's not a problem. Some real-time algorithms, such as Vibe, are good enough for this method. But for semantic segmentation, the real-time networks are not as performant, which unfortunately is not enough for SBS. Then, what do we propose? Well, we propose to compute semantic segmentation less often and find a faster surrogate for the semantic information simply when it is not available. To do so, we integrate to SBS a change detection algorithm to know whether or not we can trust the previous semantic information. The decision table now looks something like this. The change detection algorithm indicates whether or not the pixel and its surroundings have significantly changed from the last time semantics was available. If the pixel has not changed too much, we can still trust the previous semantic information and apply its decision. This is shown in orange in the table. Otherwise, we do not trust it and rely on the decision of the motion detection algorithm just as before in blue. All right, let's take a look at the performances. We evaluate our method for different semantic frame rates, starting from each image having access to the semantic information to only one semantic information every second. As you can see, our method increases the performances compared to the original algorithm for all semantic frame rates and gets performances close to the state-of-the-art ones while being real-time. If we take a look at some motion masks, we can see that they are now way closer to the ground truth with our method. The improvements come both from the background and the foreground. For example, the moving leaves in the tree are not considered in motion anymore, and the cars and people are better segmented overall. This makes our method useful for many applications. For instance, video surveillance systems need accurate real-time motion detection to trigger alerts. And since they usually do not have high computation power, it is important to be able to reduce the semantic frame rate without degrading too much the performance. This type of motion information can also be used in more complex AI applications, such as attention mechanisms. Well, anyway, if you are interested in one of these applications, you can try it out since our code is available on GitHub for the scientific community. Just please know that this work is patented if you are ever planning on commercializing it. Okay, so now we know how to get motion detection in real time. Let's tackle two other types of low-level semantics that are meaningful in the case of soccer videos: player segmentation and detection. These two tasks are often tackled by supervised deep learning models. And just like the motion detection algorithms that we've seen, there is often a trade-off between the speed and performance of such models. But on top of that, the supervision also adds an extra trade-off related to the good or the bad generalization on unseen data. This means that you must make sure that your model works well on each new game, even if the stadium or the player jerseys changed. We tackled this new trade-off by proposing an original way to train deep learning models. Usually, when developing a deep learning solution, like for segmenting or detecting the players, we have to go through 4 phases. First, we select or create a dataset containing annotated data that we split into a train, validation, and test set. In the second phase, the train and validation sets are used to tweak and train a model through some kind of iterative process. Once the model has reached acceptable performances on the validation set, we can move on to phase 3, the evaluation. There, the objective is to get a metric that reflects the performance of your model on unseen data. Most research papers stop at the third step and simply report the results obtained on the test set, and honestly, that's usually fine. But for industrial applications, there is actually a 4th step that we choose to call inference. This is the practical use of your model in a real-world environment. Usually, the same model than the one from the training and evaluation phase is used. But the distribution of this new data might be different than the one from the dataset. And if the distribution changes, there is no guarantee that your model will still work well, which is of course a problem. A last issue with supervised approaches is that they need annotated data, which takes a lot of money and a lot of time. With our method that I'm about to present, we can train a model without manually annotating a single image. Let's see how. The first important component is a student network that is fast enough to work in real time. This network will make the inference on all frames of the video. But unlike what is usually done, we will let the model evolve during the video. To do so, we introduce a massive teacher network that is able to perform the same task at its own pace to produce some surrogate ground truth. This teacher network has to be both performant and universal, meaning that it should already generalize well on any data. These ground truths are then stored in an online dataset that is updated with new images coming from the teacher and all the ones removed. This online dataset is then used to train a copy of the student network. Please remember that this is all taking place in parallel to the real-time inference. All right? So at each epoch of training, the weights of the students are updated, and it thus gets better and better on the specific game that it is supposed to analyze. This way of proceeding has some huge advantages compared to the traditional training methods. First, we can choose any architecture for the student network that fits our specific hardware needs. So for instance, if you're working on a large computer server, you can use quite complex student networks, as long as they run in real time on your video, of course. And if you're working on a smaller embedded device, you just need to choose a smaller architecture. Then, For the choice of the teacher network, simply take the best network that is able to run on your device. It can be as slow as it needs to be, as long as it gives good predictions on your particular data. Then, with the remaining of the computation power, simply find the appropriate update rate for your student network by choosing the number of samples kept in the online dataset. This online distillation method is actually quite generic and can be adapted for many different tasks on many hardwares. For the results now. What we hope to get is for the student network to get better over time, just as we said. And when initializing this student, we've got two options. The first option, which is shown in blue, consists in choosing a student network with random weights. So at the beginning of the video, the network has no idea of what the video represents or what it is supposed to do. But thanks to the online distillation, it should gradually learn to perform its task on this video, which will eventually lead to good performances. The second solution is to start with a pre-trained network that was trained with the usual approach that we've seen. If we do not perform online distillation, the performances might look something like the gray line. So mostly static, as long as the video conditions remain stationary. But if we allow this same network to train using online distillation during the video, its performances might improve, which is shown in orange, and that will lead to a gain compared to the static network. But wait, there's more. The conditions may change during a video. For instance, in a soccer game, it can start snowing at some point. Maybe the static network was not trained to handle the task during snow. Its performances will decrease as snow is building on the field. But our student network can make up for that by training on the new snow images. Hence, its performance will drop just the time it needs to learn how to handle snow, and then the performances will increase again and stabilize. This is also relevant for video surveillance. So for instance, in the summer, a lot of parasols can be put on public places, and that can disrupt a static network that has never seen those. Alright, let me now show you that our method works for a practical case, segmenting the players on the soccer field. As we can see, the evolution of the performance is just as we predicted. The performances increase during the video for the network trained with online distillation and are somehow stationary for the static network. Also, we can see that during the game, there is an unusual event, corresponding to a dispute with some bear mascots just outside the field. The performances drop during that time because neither the student or the teacher has ever seen such a bear. But our student network is still able to recover easily after the dispute ends, and even kept on learning throughout for the most important parts. This shows how robust our method is, even when unusual events are not correctly handled by the teacher. If we do a side-by-side comparison of the results of the static network compared to our method, we can see that our student learned to better segment the players than the static network. In other words, it has become specialized to this particular game, and this increases its performance. We can also see that our segmentation method can be adapted for various situations, like player segmentation in basketball or car segmentation from a surveillance camera on a busy Japan crossing. As we said, the core principle is actually quite generic. Let's now look at another example in Times Square, New York, where we want to segment all passers-by. We start from scratch and let online distillation do its job, just like we would do in a practical setup. Simply place the camera and let the network learn. So at the beginning of the segmentation of the video, the segmentation is of course not good, but it gets really good over time. Then, at some point, someone changes the place of a parasol, which changes the video conditions. This perturbates the student network around that area. But after the parasol is put back at another place, the student simply adapts and reaches good performances again. As an extra result, we also notice that sometimes the student network is actually better than its teacher. As you can see, the players on the wall are better segmented with our student than the teacher. That's a bit weird, right? But we believe that this is all thanks to the simpler architecture of the student network that we use, which allows it to smooth the random errors of the teacher. I really like this project a lot, and I think it has some great potential for further applications, which is why I guess it received the Best Paper Award. If you want to try it out on your data, we made our entire code available on GitHub. All the links are in the description below. With these links, you have access to the real-time implementation that you can directly integrate into your own projects. And speaking of projects, we actually already tested online distillation in a practical setup during my research stay at Aalborg University in Denmark. In this project, we set aside the professional stadiums for a while and focused on lower budget soccer fields, just like the ones you can find in your hometown. The objective is the following. We want to detect all players on the field. That means placing bounding boxes around them to count the number of people using the field, which allows to automatically monitor the use of the facility. Of course, we don't want the budget to explode, so we need to work with some low-cost hardware. A solution, if you want to capture the entire field at once, it is to use a single fisheye camera. Unfortunately, there exists no off-the-shelf pre-trained network for these type of images that work well. So it seems that there is no way of having a universal teacher as before for fisheye images. Or is there? In the previous work, we saw that the teacher and the student worked simultaneously on the same video. But this is not a fundamental requirement. Actually, we can use two separate feeds and simply find a better modality for our teacher. Fortunately, there happened to be an additional thermal camera just next to the fisheye one. These cameras are robust to different weather conditions, and the players are then easy to spot. More importantly, there exists some very good pre-trained network that we can use as teacher. The only issue is that they only cover a very small portion of the field, and since they are more expensive, we cannot afford to put several cameras to cover the whole field. With this new modality, the online distillation setup looks something like this. The objective of the student is still to do its task in real time. So in this case, detecting all players on the fisheye. But now, the teacher network works on the thermal video. So we just need to add some modules to transform the information from thermal to fisheye, and bam, you've got your setup. So, just as we said, we need to transfer the thermal information to the fisheye domain in order to train our student. To do so, we can easily register both cameras once using simple homography and camera parameters. This allows us to transfer the bounding boxes in between modalities. And that's great, but actually, the ground truths are only produced in a portion of the field seen by the thermal camera. This means that we are able to train our model, but only inside the common region of both cameras. If we leave it like this, the student will never predict players outside of that region. So what we need to do is to add two things outside of the common region. First, some true positive players with known bounding boxes, and second, some true negative areas where we are sure there are no players. Since we know from the teacher where the players are in the common region, we can simply crop them and copy-paste them outside of that region. This creates fake players, but with known bounding boxes. But of course, given the distortion of the fisheye lens, we must rescale, rotate, and somehow blend the crops appropriately so that the resulting image looks more realistic. For the true negatives, we use motion detection, and particularly our best friend Vibe from before, since it is very sensitive to movement. So, where Vibe has not predicted any motion, we are sure there are no players at all. And that's it. We now have true positives and negatives outside of the common region as well. So using registration at the output of the teacher and data augmentation with motion detection when training, we are able to provide the copy of the student with relevant images. And thus, the student should get better and better as the video goes on. For the experimental results, we checked that the performance increased both inside and outside the common region, which is the case. And if we take a look at the players that are outside the common region, our network is able to detect them. This is a very nice result, and it shows how powerful online distillation can be in various situations. So with that, I hope that I could give you some interest in online distillation. I guess that the scientific community is also receptive to this method, since this second work also received a Best Paper award. If you want to try it out and to play around, our code is also available on GitHub. Alright, so this closes our first part on low-level semantics. We've seen that we are able to extract motion from videos and to segment and detect objects in real time. Now, we will see what we can do with this information, moving on to high-level semantics. Let's leverage low-level semantics to interpret the game, and particularly to segment the video into different game phases. This is the first work that I've done in my thesis, and it also received the Best Paper award, but this time I promise it's the last one. So in this work, we define 4 different game phases: attack, defense, middle game, and goal or goal opportunity. Let's see what they look like. For the attack, the players are usually all close to the great rectangle and seem to be clustered and moving towards the goal. For the defense, it's basically the same kind of view, but now the players seem to be further apart from one another. In the case of a middle game, the camera is more or less centered on the field, and nothing really exciting is happening. And finally, for the goal or goal opportunity, the camera is mainly centered on the goal. Just by looking at this, it seems that we already have what we need in information about the part of the field and the camera that is filming, and simply use the position and movement of the players as well. This motivated us to build a simple decision tree to segment the game phases that only asks questions about the type of view and the players. All these questions can be answered from low-level semantics. Let's see how exactly. First, for the camera view, we can simply use a segmentation mask of the field, which can be obtained really easily using its green color and just removing the players and the lines. Then, from the shape, we can directly classify different types of view. If we segment the lines and the players, we can use first a simple ransack algorithm to extract the largest ellipse, which tells us of the presence of the main circle and gives us a good reference point on the field. And finally, for the player mask, we can extract their mean position and direction alongside a group measure to see how close they are one to another. And there we are. We've got all information we need for our decision tree. Here, you can see the players in yellow, the main circle in black, and the predicted game phase on top of the video. Just so you know, we achieve a bit more than 90% accuracy on our test set. I really like how simple this work is. It shows that we can achieve great things with some low-level information and very few annotated data. Of course, this is just a first way of proceeding to retrieve high-level semantics, and we'll see another one in the next work. we choose to tackle a major challenge in computer vision and deep learning: action spotting. Such a task cannot be handled alone, which is why we teamed up again with Aalborg University and our new partner, KAUST from Saudi Arabia, for this project. The objective is simple: retrieving the exact time at which each actions occur. For this task, we can count on the largest soccer dataset available, SoccerNet. This dataset is composed of broadcast videos of 500 complete soccer games, which adds up to about 800 hours of videos. And it is annotated with more than 6,000 timestamps of goals, cards, and substitutions. To solve this task, we now choose to go with an end-to-end deep learning approach, since annotated data is available. So our network takes the videos as input and extracts some features with a spatiotemporal analysis. These features are then sent to a segmentation module whose job is to capture the temporal context and then send this information to a spotting module that retrieves the exact frames of the actions. The main novelty in this work resides in the way we capture the temporal context inside the segmentation module. Let's see how it works. We start by defining 6 temporal segments around each ground truth action spot: far before, just after, far after, and some transition areas. We use all these segments to define our training loss to induce different behaviors in each segment using a time shift encoding. This basically tells for each frame how close or how far they are from the closest actions. For the frames that are far before or far after an action, we train our network to avoid predicting an action. That makes sense, right? Now, for the frames located just before an action, we cannot predict if the action is going to occur. If you think of a player that is approaching the goal, you can't know for sure if he is going to score. Hence, we do not penalize the network. Zero loss, it can predict whatever it wants. However, just after the action, the network must be able to identify its occurrence, and this fades away as time goes. Finally, we parameterize the loss in the transition areas such that the loss is continuous between the temporal segments. And that's it. Our loss now looks like this on the left for a single action, and like the one on the right when several classes of an action occur during the video, such as several goals. Basically, the loss is constructed smoothly around the actions. For the action spotting module, we split the video in chunks. For each chunk, we try to spot the action that it contains, if any. The actions are encoded with a set of vectors, 1 per action, limited to 5 actions per chunk. In the vectors, we encode the presence or absence of the actions, their location within the chunk, and the class of the actions, so in our case, goal, card, or substitution. To compare the predictions with the ground truth, we leverage an iterative one-to-one matching to pair each prediction with a ground truth vector based on which has the closest location in the chunk. The action spotting loss between the predictions and the ground truth vectors is then computed as a weighted sum of squared errors. On the SoccerNet dataset, we beat every other method by far, making it the state-of-the-art for action spotting. In the rightmost graphs, we plot the segmentation score in orange, the ground truth by the blue bars, and the detections with the green stars. Everything seems to work fine. We have a majority of good detections around the actions, with sometimes false positives or false negatives. But we notice some irregularities in the segmentation score. At some point, the segmentation score increases for one class, but without giving a detection. So we took a look at the original videos at that moment. Most spikes from the goal class correspond to goal opportunities, and the majority of spikes for the card class correspond to unsanctioned faults. This is a nice result, as these events are not annotated in the dataset, and we now have a way to retrieve them. As a use case, we choose to produce automatic highlights, as these kinds of actions, along with the cards and goals, are often shown in highlights. As always, our code is available on GitHub and has already been tested and approved by a foreign company. Alright, this is awesome, but isn't the playground a bit too restrictive? We have 800 hours of video, which is huge, but we only have access to 3 classes: goal, card, and substitutions. Well, this is exactly why we teamed up again with Albor and Kaust to extend the SoccerNet dataset. In this new dataset, we push the original 6,000 annotation to 300,000 and propose 3 tasks in total. The action spotting task that we of course keep from the original dataset, 2 subtasks related to camera shots, so with temporal segmentation and boundary detection, and finally a whole new task of replay grounding, which aims at linking each replay shown in the broadcast to its corresponding actions during the live game. For all these tasks, we provide some benchmarks that will soon come along with public codes and leaderboards. Let me just tell you that I will present a few extra results than what is originally written in the thesis. That's because we kept on working on this subject after it was released, and I just needed to show you what we achieved. But don't worry. We published all those results in a new paper that is available on arXiv. So make sure to check it out after the presentation if you're interested. Alright, so back to the tasks, data, and benchmarks. We'll start with the one we already know, action spotting. The objective is still to spot the exact frames of the actions, but instead of having just 3 classes, we now propose 17 classes in total, including all actions that typically occur during a game. This adds up to more than 100,000 annotations, which contain the action class, of course, but also the team and a new shown or unshown tag that basically tells you if the action was visible in the TV broadcast. This last tag brings a new interesting analysis to the spotting results. To have a high performance, the algorithms can not only rely on visual cues anymore, since they have to spot unshown actions as well, based only on the context. For the results, we of course tested our context-aware network, and it provides the best results overall. To go further, we also re-implemented and adapted several methods that produce some results on SoccerNet v1 to test them on our new dataset. As you can see, there is still a large progression margin that can be made, especially for certain classes that seem to be more difficult to spot, like indirect free kicks or shots. We also noticed that there is a gap between the shown and unshown actions, which suggests that there is also some improvements to do on context aggregation. Now, for the camera shots, just as we said, we separate this task into 2 subtasks. So first, segmenting the different types of cameras that are filming the game. For that, we annotated 13 different classes, including less represented cameras such as the spider cam or the camera inside the goal. And second, we have detecting boundaries between the camera shots, which can be of 3 types: abrupt, when switching directly between cameras, or logo or smooth, as represented on the right. This type of semantic information is interesting for the automatic production of games. So for example, knowing which camera is shown and when it changes opens the path for further applications in this domain. As a final annotation, we also state for each clip if they show a live event or a replay of an action. This will be useful for our final task, but before we talk about that, let's first see some benchmark results for segmentation and boundary detection. We also adapted our context-aware method since it has a segmentation module that can be used for the camera segmentation, of course, and a spotting module that can be used to detect the camera shot boundaries. For the segmentation, our method provides the best results compared to simple baselines. But for the camera shot boundaries, some other methods from the literature have a higher score. We can nonetheless note that ours provide the most consistent results across all transition types. Alright, the final task now, replay grounding. The goal of this task is to link each replay to the live action it shows in the entire untrimmed game. This is a particularly difficult task, since in the replay, the action is often shown from a different point of view and can be played at a different speed. We propose a simple solution to get people started on this new task. Once again, we use our good old context-aware network and adapt its input to a structure similar to a Siamese network. The principle is simple. We compute features for the replay and some video chunks with the same feature extractor, and hope that when the video shows the same action as the replay, both features are similar enough to trigger a grounding prediction. Using this simple adaptation, we are able to reach quite promising results, showing that our task is manageable, but that it will be a great challenge for future methods. There, you can see a practical example where the replay of the goal is located at the end of the video in red, and the linked action is at the beginning in blue. As you can see, our method is able to retrieve it. The plot shows just a little green star above it, and unfortunately we also have two false positive predictions in the middle. These two actually correspond to two other goals, which are very similar to the one from the replay. As I said, this task is still a bit challenging. Alright, so now you have a pretty good overview of our new dataset and its tasks. If you want to see it for yourself, you will soon be able to download it directly from a pip package in Python, which has been amazingly made by Silvio Giancola. Make sure to participate in our Open Challenge that will be open at the beginning of next year. The best methods will be presented in a prestigious workshop in 2021. Now, it's time to wrap things up. Well, we covered quite a lot of material today, starting from low-level semantics such as motion detection, segmentation, and detection, all the way up to high-level semantics like the game phases, the game events, and finally, our novel dataset containing many information about the game and the broadcast itself. I want, of course, to thank all my co-authors from Liège, Louvain, Albor, and KAUST, who have been amazing partners in this wonderful journey. As I've already said, most of our work is available on GitHub in the Python language, so feel free to play around and try it on your own data, as many have already done. Finally, if you want to know more about our research, make sure to subscribe to our YouTube channel called ACAD Research, where we explain our different work among some other cool things. Well, thank you all very much for attending this presentation. I was not expecting so many people both on LifeSize and on YouTube, and it's truly been a pleasure to present my thesis in these conditions. Now, dear President and members of the jury, I will be happy to take your questions on LifeSize. Thank you all. Have a nice day. Bye.